landslide track.
Yeah, landslide track. We gave it just an imaginative name, just in case people get confused. Alright guys, I'm here to talk to you about the landslide track we created, something that tracks landslide. Can look at the screen. Alright, so you can see it here. Basically what it is you input some GPS coordinates, or it takes them from where you are, and then it can give you sort of your risk of having a landslide. And we've figured out sort of your risk of having various different landslides, but essentially, having a landslide in maybe next few weeks. It's not so much of an immediate one, just if you're in a landslide area. Okay. Anyway, okay, so landslides are actually a reasonably largest problem that I don't think many people think about. There was quite a really recent landslide in Washington just last month that killed around 20 people, and there have been 20 landslides just in December of last year. And approximately about 600,000 people die every year because of landslides. So it's a largest problem that I think modern people consider when they consider natural disasters. So when they're trying to prevent landslides, they tend to do a risk assessment. So that involves sort of evaluating the environmental factors, that's like the land, the geology, considering like the structure, what kind of soil it is, and the height. And then they sort of consider triggering factors, which are obviously things like earthquakes, or maybe large amounts of rainfall. And then they consider landslide inventory, which is how many times there's been a landslide previous, which is quite an obvious one. So we sort of try to take advantage of that. But what they often do, that we have done it, often don't do in ours, we have done in ours, is they use spatial predictions, which means they look at the area that they're directly in and use that to make predictions, whereas we used sort of previous happenings of earthquakes to try and predict whether there would be landslides, because a lot of their risk factors are trying to find out whether there will be a landslide in the next 2 or 3 days, whereas we were looking at it more as people could use it to find out if they were in a landslide risk area, and so whether they'd want to be there. And additionally, they always try and use one statistical model to try and predict all the different types of landslides, which, as you will see, next slide, yes, there are quite a few. Okay, it's quite actually hard to categorise landslide types. This is a really basic idea of some of them. We just picked 3 because we thought they were the easiest ones to predict with the data we have. But so because they try and look at the sort of gradient of the land the landslide's on, and the type of soil, and what kind of things are impacting it. And so the 3 we picked are fall, which is basically due to a really steep gradient, like a cliff edge, that's going to be set off by an earthquake or something. It's not very impacted by rainfall at all. And then you've got flow, which is a much more steady one, but it is impacted by rainfall a lot, hence the name flow. And topple is sort of somewhere in the middle, we decided. I think they're both somewhat influenced by how much recent tree felling has been going on, but not as much as there is with the water and the gradients. Okay, and these are all the predictors that they use in their models, and you can see it's absolutely massive. When we made our model, we were unfortunately constrained to much fewer data types, so we chose to use internal relief for our sort of using for the gradients and trying to predict how high the hills were and where you were in relation to that. We were unable, unfortunately, to use actual structural sort of soil things, so we used seismic data of previous earthquakes, which is why we're using temporal data, and they were using spatial data, because we've been using the history of earthquakes. And additionally, we were unable to find the water table data, so we used recent rainfall. So those were the things we used to make our predictions. Alright, and these are the equations we used, which I'm going to skim over, but essentially we made quite a few equations for sort of predicting how much the earthquakes that were recently there would impact it, depending on the distance and how strong they were, and those are our distance equations. So they were sort of roughly figured out, so they'd be approximately what we expected. Okay, cool. Anyway, I'm going to tell you how we built our various models. We, for the fall, I think that's the fall. Right, you can talk about equations if you want, but yeah.
Okay. No. I'll just nominate you just into that.
Oh, okay, no, the fall.
Go back.
Right, keep. Okay, so for fall, we tried to look at the gradient and see how steep it was nearby, and then we considered the seismic data. For flow, obviously, we took into account rain much more and gave that a heavier weighting. We were still trying to take into account a sort of slightly less steep gradient. obviously if there was no gradient whatsoever, we were completely ignoring it because there's no point assuming a landslide when there's a flat surface, you know? And topple, we sort of gave it the various estimates. So I think we can go to the end. I can tell you about the problems we have now. Unfortunately, we did not have a web server, so a lot of the data, because we made it as an Android app, we were unable to have large amounts of data, because obviously we had to load it from SQLite, so it had to be much smaller. So we have managed to get coordinates for all of America, but not anywhere else. We're able to predict if you're going to get an earthquake in America. So we have the rainfall data there and the gradient data there. Additionally, we had a lack of testing against proven data, so obviously our equations are somewhat rudimentary. They do give you a reasonable answer, but obviously we haven't been able to test them to refine them, as in database hosting. If we'd had a database, we'd be able to have much larger data sets. And additionally, our gradient estimations, we're only able to take a few coordinates to predict the height of the gradients. And if we'd been able to take more coordinates, it would have been a lot more accurate as to how high we were when we were existing. So we've sort of got a bit off skew there. I think that was everything that we can demonstrate the app to as well, because we have that capable of it. Yeah. Do you guys have any questions about landslides while waiting?
You said you were coming up with your own weighting, so how do you justify that?
How do we justify that? Well, having read up around it, we were able to find out what kind of, how heavy the weightings would be for certain, obviously, the water was much less so for stuff like fall, so we would try and ignore that as much as possible. But it's still true that a heavy rainfall would be a trigger, so we incorporated it to a very mild extent, I think. I mean, like,
We-
develop the equations.
Yeah, okay, so what we were comparing to was sort of, we looked at some historical data of where there had been landslides and what our values would be. And we found that, so we ended up with essentially three weightings. One for how likely an area was to have an earthquake, how likely it was to have a lot of water, and how steep it was there. And then we looked at areas where there had been landslides, and we saw that in areas where it had been categorised as a fall, that it was very steep gradient, but whether there'd been a lot of rain or not didn't seem to matter. Whether there was earthquakes didn't seem to matter. Sometimes they might have acted as a trigger, but there were plenty of occasions when they didn't. And similarly for topple, we found that the topple one was much more likely to happen when it was fairly steep and there had been an earthquake. Didn't and only seemed to care a little bit about the rain. And then the flow one, we found that when we compared to historical data, we just saw lots of flow, we saw lots of rainfall, and it being moderately steep, earthquake data seemed to impact it a little bit, but not greatly. So it's more likely to happen in areas where there were plenty of earthquakes, but it certainly happened in areas where there weren't any. And so we just sort of came up with sort of heuristic values for each, to combine our three things. For topple, I think we multiplied them together. For flow, we added them together. And we found that those values coincided with areas where there had been landslides in the past, and so we felt that that was a reasonable predictor of landslides happening in areas where those values were high. Certainly we would need to do more work to more accurately parameterize these values. In some ideal world we might look at some pattern recognition, but we didn't have time to do that.
Thanks.
Anyway, this is our application. As you can see, you enter the latitude there and the longitude there, and you can choose the range at which you're sort of wanting to look around. It goes up to 10 kilometres, yeah. And then you hit and you'll get a risk factor here. Were there any more questions on the way?
Yeah, just who's the application targeted at?
The application targeted at. We were thinking of people that might want to be aware of earthquake risk, landslide risk within their immediate area, like not particularly high level, just sort of people that might be like, oh, landslides, you know, and sort of be able to maybe consider whether we're moving. They could look at that. I mean, yeah.
Insurance companies?
I reckon that maybe you're using a slightly more sophisticated
Yeah,
I'm not going to lie.
With more sophistication, yes, insurance or city planning. For example, if you know you're in a high-risk area, you want to be really careful not to do further deforestation or further mining, which are common human triggers. I mean, in general, one of the things we haven't accounted for here, but we considered accounting for, was human population. In general, if there's lots of people there, they do something to mess up the local area and increase the risk of landslides. And sadly, that seems to be the case even in the developed world, where we think we might have got better at these planning issues. So yes, with further development, it could even be useful for that. At the moment, we wouldn't want anyone making any planning decisions based on the current policy.
But that is a huge risk, though. If you remember a few years ago, there was a case in Italy where some geologists said, I know there'll be a few tremors, but don't worry about it, there's not much chance of an earthquake.
And then
there was a massive earthquake, and they actually ended up in prison. So
where
you guys going to enter me prison here?
I have to say, from my point of view, having done science, the fact that the Italians imprisoned scientists for making the best judgment that they could, that was outrageous.
They're still in prison now.
It's a travesty of justice, and we're not in Italy, and I would be fairly confident outside Italy we would not have to worry about that. But anyway, as it happens, our data so far only does the USA. If we have to, we'll just not ever allow Italian data to be submitted to us.
So yeah, you can see here it's being able to state that the probable landslide, which is high risk, would be a topple one. Sorry, stays there. Sure, we've exhausted all your questions. So if you want to
No,
tell us,
just interested in where it goes from where it is right here. What would you your next set of improvements be?
Yeah, that's easy. We would totally like to get a server up and running. We'd much rather have data that didn't just involve the USA. I mean, so it'd be much more interesting to have a wider range. We'd obviously love to refine it and test it against real data and find how accurate it was. There's easily another set of algorithms we could put in with forest data. We'd really like to add that in because whilst it's a minor factor, it's still important. And the big one that we'd absolutely love to have is the structural data of the material in the soil, because that's really important. We just couldn't find anything like that. And we couldn't have parsed such a large file even if we did have it.
We could find some data that was commercial and would have cost a fortune. Obviously, we were not prepared to spend thousands of pounds to get the data for this. But if we were further developing this for actual real use, then of course we could include much higher resolution data.
Yeah.
So,
that would definitely be easy.
So for example, here when we're calculating the local grade use, we do this by randomly choosing points within a few miles and comparing the height, because unfortunately the resolution of these data sets is normally far too coarse for us to look at sort of a normal finite difference, go a bit to the right, a bit to the left or down. So we sort of look at the local area, and if there's a wide variation, which is why we call it standard deviation, then we consider that to be a hilly area, and if there's a small deviation, then it's a flat area. But obviously, in an ideal world, we could do something with a much finer resolution. We do, because we can only call the standard deviation a small number of times, there's a large error bar on this, so running the same place twice, you'll get significantly different values.
That was significantly. I'm sure they'd stay high risk.
It would definitely stay high risk,
but
it might be a change from it being 17 here to it being 20s, or it being maybe close to 10.
And you can probably see the rainfall index comes up as NA quite a lot. It's because we only have single coordinates for the rain. We don't have sort of floats for it. And if we did, then we'd actually be able to get more rainfall sections. There you go. Those are easier improvements. Okay, all the time. Okay. Is that everything, yeah?